Good morning, students. Hopefully, you are doing well. Welcome in next lecture of Math F242 Operation Research. Presently, we are doing simulation. Last class, we have covered the simulation of single server queuing system. Hopefully, there is no doubt. Still, if anyone has a doubt, please ask because it is very important topic. Audio video is okay.
Yes, sir.
If you have a doubt, let us continue with the last lecture. Simulate a single server queuing system. First come, first serve, interval, and service time are exponentially distributed with mean 1 upon 2 and 1 upon 4 respectively, and with unlimited supply of customer and with a maximum allowed queue length to be 4. So when we have the restriction of allowed queue length to be of 4, it means this implies this is the interval time exponentially distributed. So m service time is exponentially distributed. It is again m. Single server FCFS capacity is given to you as a queue length is given to you as a maximum 4, one with service. So m will become the 5. So when the m will become 5, and here the population size is given to you infinity. So it is nothing. It is the single server finite capacity model. It is single server finite capacity queuing model. So now you have to simulate for the 5 unit of time, means this is given to you as a t max. Assume that first customer arrive at the 0 time, means you can say initially there is one customer. Initially there is one customer, one customer, because when we are starting our clock there is one customer. So here from in the question it is given to you 1 upon lambda is equal to half and 1 upon mu is equal to 1 by 4. Mean time is given to you. So from there we can determine lambda is equal to 2 and mu is equal to 4. Lambda is equal to 2 and mu is equal to 4, and t max is given to you as a 5. So clock start from the 0 time. So at that time current event is the start of the simulation. This is the CNA. So CNA will be the 0, CND will be the okay. We have not taken the that part here, right? In the simulation table, in the solution, yet it is given to you, but I have not taken in the solution. So you assume that there is no customer, right? In this, you assume that there is no customer. There is no customer at t is equal to 0. So when we take so at the t is equal to 0, when there is no customer, it is 0. It is 0. NS is equal to 0, right? NQ is equal to 0. Then CWTS is equal to 0. CWTQ is equal to 0. STS means server is ideal. CIDT is equal to 0. So we have to generate the new arrival, right, or the first arrival. So for the first arrival we are taking the random number 660. So when we take the random number 660, so using the formula 1 upon minus 1 upon lambda ln of ua, you will get the interarrival time as a 0.208. So next arrival time will become 0 plus 0.208 is equal to 0.208, because it is the first customer, right? So first we want the it should be 1 minute, it should be infinity, it should be the infinity. So when we are it is the first customer, so we want the first arrival. So net will be the minimum of 0.208 infinity and t max 5. So first event will be the arrival. So at the time 208, at the time 208 we have the arrival. So number of customer in the system will become 1. CND will remain 0, NS will become 1, NQ will be the 0, right? Then we have to update the CWTS, CWTQ. Now server is busy with customer, so it is 0. Now the CIDT, so CIDT we have to update. So for the time to 0.208 unit of time, right? Server is busy. Then because it is the arrival, right? So we have to generate the new arrival and departure also. So we are taking the random number 657. So corresponding to 657, our IIT will be the 0.210. So when we add 0.210 with 0.208, so you will get the 0.418. And because we have already the one customer, so we have to generate its departure time also. So we are taking the random number for service as a 985. So corresponding service time is the 0.08. So we have the 0.215 NDT. So minimum of the 0.215 and 0.418 and 5 will be the 0.215. So at the 0.215 we have the departure. So when we have the clock time 0.215, we are writing the departure. So here the CNA will be 1, CND will increase by 1, right? Now NS is equal to 0, NQ is equal to 0, and total CWTS you have to update, NQ is equal to 0. Now again, because there is no customer, again the server will become the idle. So now we have to update the IAT. So because of the departure, we have to generate the new departure time, new departure time, and previous arrival we have to continue. So 0.418 will be the next arrival time, and we generate the next departure. So next departure is the 1.018, right? So minimum will be the 0.418. So here we have the arrival. So when we have the arrival, right, when we have this arrival, so again at this point we have the arrival, uh, right? So continue, you can continue. Then due to the arrival you have to generate the next arrival time, right? So again the minimum is the 0.572. So next is also arrival, next is also arrival, next is also arrival, next is also arrival. So due to the continuous arrival, what will happen here, the number of here the number of, right, and number of the CNA will become the or NS, NS will become the 5. So when the NS is equal to 5, so what will happen here, the whatever the new customer, that will become the lost customer. Means because of the because of the limited space, now customer cannot join the system. So here we write the lost, because it is neither the arrival nor the departure, so it is the lost. Again the customer is coming, and that customer is also the lost. Then after we have the minimum at the 1.018 we have the departure. So due to the departure, now we have the empty space, so we allow the arrival, we allow the arrival. So that is the update when we have the finite capacity model. Nothing we have to explain much, because how the table is going on, that you can easily write. But when we have the limited capacity, so at that time, instead of the arrival departure, you have to add one more event, that is the lost. Clear? Clear? Any doubt?
See, sir.
Yes.
Sir, in exam or quiz, how will we get a problem on simulation? How will it be? Should we form the table, or how will it be? How will the questions
No,
be
no,
asked?
that I will take care. That I will take care.
No, sir. I just
It is
want to know what kind of question can be asked. I just want an idea for it.
means I will write the situation. Then what will be the what will be the result for that situation? That you have to write. For
So, will it be like I have to form the table like the 12 columns with some amount of
no,
columns
no,
you've
no,
written?
no, no, no. That you cannot draw there.
Okay, sir.
That kind of the table you cannot draw. Just one more thing I have to explain. Actually, I'm not able to. So this we have taken the question from this book only, 9.8. Now, so instead of the single server, by chance, if we have the two servers, you have to make in the same fashion only, right? This is the table 9.10. So instead of the one server, now you have to consider the two server, right? So here the random number for the first server, then its service time, then NDT, right? Then after it is the random number for the second server, then ST, then the NDT. Whether the first server is ideal or BG corresponding, we have to compute the cumulative ideal time. Whether the second server is ideal, and corresponding to that, we have to compute the CIDT. So otherwise, everything is the same here. Clear? So means if there are the two customers, then only both server are busy. If there is only one customer or zero customer, accordingly we have to decide which server is busy, which server is ideal. So that is little update. So when we have the so you can read this from your book. It is the solved example, right? So you can read from the book only. So we can have the multiple server also. Clear? So as I have told you, if anyone has the interest, please make the computer program. It is very interesting thing. So you can make the computer program and you can simulate the queuing system. Now we have the new chapter. So this chapter we are taking from the Operation Research Taha book, right? It is exactly the same book whatever you have for the optimization course. So next chapter is the game theory. Game theory deals with the decision situation in which two intelligent opponent with conflicting objective are trying to outdo one another. For example, in cricket, we have the two teams. Both want to win, right? Both want to win. So both team have the some specific strategy. Some particular team has a good batsman, some particular team has a good bowler or fielders, right? So different strategies we have. So using those strategy, both team want to win the game. So that is the in that we are saying the intelligent opponent. Intelligent opponent means depending over the strategy of the opponent, we can decide what can be the best strategy to win the game. That's why we are saying that intelligent opponent. With conflicting objective. Conflicting objective means both want to win. If means if we can have no conflicting objective means we have the same objective. We want to win means we want to do that work in optimal way. So both want to do the particular work in optimal way, then it is not a conflicting objective. But here the conflicting objective means both want to give win, right? So when one opponent is winning, then naturally another opponent is losing. So are trying to outdo one another. So both want to win over the other one. So that will be studied in the game theory. So in the game theory, as you have seen, we have the two players. In game conflict, we have the two opponents known as the players, and each have the either the finite or infinite strategies, means with which he can play the game, means alternatives. Each player has the finite or infinite alternatives. Then number of alternatives or the that alternatives are known as the strategies. Associated with each pair of the strategies, the payoff or that one player receive from the other. So for example, if I say player A is using the ith strategy and player B is using the bth strategy, jth strategy. So with the combination of AI and BJ, naturally there is a payoff. Payoff means either A has to give something something to the player B, or player A will get something from the player B. So either there is the loss or the profit or gain. Either there is the loss or the gain. So that is the payoff. So such games are known as the two-person zero-sum game. Why the zero-sum game? Means whatever you are getting, right? Whatever the player A is getting, that is the loss of the player B. Whatever the player B is losing, that is the gain of the player A. So it is the zero sum game, two-person zero sum game, because the gain by one player signifies the equal loss to the other. So it is sufficient to summarize the game in term of payoff of the one player. So it is sufficient that to represent the game problem for the one player, either for the player A or for the player B. Means whatever the gain of the player A, automatically that is the loss of the player B. So need not to mention the payoff matrix for the both player. If you are mentioning for any player, it automatically it is understandable for the another player also. So designating the two player as a and B with M and N strategy respectively, the game is usually represented by the payoff matrix of the player A. So generally we write the matrix for the payoff matrix for the player A whenever we have the two players, player A and player B, having the finite number of strategies, maybe the infinite also, but having the finite number of strategies, M strategies or N strategies respectively. So how we can write the payoff matrix? So this is the way to write the payoff matrix. Means these are the alternatives of the player A. Here on this side we have the alternatives of the player A, and on this side we have the uh, alternatives of the player B. Player B. So let's say that player A has the total M strategies and player B has the total N strategy. So corresponding to the first strategy of the player A and first strategy of the player B, we have the following payoff. Similarly, we are writing the payoff to all pairs, corresponding to all pairs. So this is the representation of the game problem for the player A. If you want to write the payoff matrix for the player B, just you have to multiply right, with the minus sign. Just you have to multiply with the minus sign in each entry. So that will give you the payoff matrix of the player B. So from this we have to compute the optimal solution. So when we have the conflicting objective, in that case what is the optimal solution? Whenever we haven't the conflicting objective, then it is simple. Either you have to maximize the profit or minimize the losses. But when we but in the game theory, what we have, one is gaining, another is losing. So if you are maximizing the gain, then naturally you are minimizing the loss, right? So no team want to minimize the loss, right? No team want to minimize the loss, no team want to maximize the loss. So in this case the optimal solution is little bit different, right? So optimal solution for the two person zero sum game will be the means it is if in general what is happening, you think about that. You are winning and another opponent is losing. So what should be your strategy? If I am winning, i I win with the maximum difference. If opponent is losing, what is the objective of the opponent? Ki if I'm losing, I lose with the minimum difference, right? So both want the best alternative, both will apply the best alternatives to minimize the to minimize or to maximize the difference, right? So because the games are rooted in conflicting of interest, the optimal solution select one or more strategy. So for the optimal solution, we opponent can or both player can choose either the one strategy or mix of the strategies, or mix of the strategies with some associated probabilities. More strategies for each player, such that any change in the chosen strategy does not improve the payoff of the either player. Means if I am winning, so I have selected the few strategies. It is decided, means it is confirmed that I am winning, and I want to win with maximum difference. So for that purpose I have chosen some alternative, right? So if I change those alternatives, naturally my difference of winning will reduce, right? So that is the optimal strategies. If I am losing, right, it is confirmed that I am losing. So if I change my strategies, so I will lose with more difference, I will lose the game with more difference. So that is the optimal strategy. Means optimal strategies will optimize the difference of winning or lose of the game. That is the optimal solution, right? It is little different from the optimal optimal profit or optimal loss, optimal gain or optimal loss. Right. So these solution can be in the form of the single pure strategy. So this can be either the single pure strategy, or it is the mix of the several strategies with associated probabilities. Means with this likelihood you use this particular strategy. So that is the optimal solution. So how we can determine the solution, that we learn here. So let us have this question. Determine the saddle point. Saddle point is the point where we have the optimal solution or unique solution. Not optimal solution. First, you say the unique solution, right? So saddle point of the game problem is nothing where we have the unique solution. Determine the saddle point solution, associated pure strategies, and value of the game for each of the following game. The payoff R for the player A is this. So this is the payoff matrix. So for that purpose, we use the principle of the best of the worst, right? If, in the game theory, we use the principle of best of the worst. First, we identify what are the worst situation. If I am using the worst strategy, I will be in the great loss. So first I select the worst situation. Out of the worst situation, I select the best one. So if this is the game matrix, if this is the payoff matrix for the player A, so what it signifies? If player A is using the A1 strategy and player B is using the B1 strategy, he will get the 8, gain of the 8. Similarly, here we have the gain of the 6 if player B is using the strategy 2. If player B is using strategy 3, then the player A will get the gain of 2. And when the player B is using the fourth strategy, then the player A is getting the 8, gain of the 8. Similarly, we have the following data. Whenever we are saying that here we have the minus, what the minus signify? That A is losing. If it is given to you the payoff matrix of player A, the minus signifies that A is losing, plus signifies that A is getting. Clear? So when we have to write the payoff of the player B, so just if it signifies the gain of the player A, it means this is the loss of the player B. So when you have to write the payoff of the player B, just you have to multiply the with the minus sign. Here, whatever the gain of the player A, that is the loss of the player B. Whatever the loss of the player A, that is the gain of the player B. Right. So here we have the payoff matrix of the players. Now, how to determine the optimal solution? That is the next part. And for that, I have told you we are using the best of the worst. So, what is the first? Means now, please pay on the word. What is the worst? If player A is using the first strategy A1, and player B has the choice of B1, B2, B3, B4. So what is the worst situation for the player A? What is means here? Here we have the gain of 8, of 6, of 2, of 8. So what is the worst situation for the player A? Means minimum gain. So here we compute the row min. Means worst situation for the player A is the minimum gain in on applying the strategy 1. It's means no matter the player B is using which strategy, but when the player A is using his first alternative, the minimum gain will be the row min. So row min will be the 2. If he is using the strategy 2, then row min is the 4. Then if he is using the strategy 3, then minimum gain will be the 3. Clear? Now, according to according for the player B, what is the maximum loss? What is the maximum loss? So maximum loss is what? Means here we compute the column max, because it is the payoff matrix of the player A. So what is the worst situation for the player B? The worst situation for the player will be the maximum loss. Maximum loss. So here the column max when we compute. So here we have the 8, right? Here we have the 9. Here we have the 4, and here we have the 8. Now we have to determine the best of the worst. So worst situation we have seen. Now what is the best? So here we have the column max. So in the column max we compute the best situation, that is the min. In this case we determine the row min. Here we have determined the row min. Now out of the row min, which one is the max? So that is the max. Means here the 4 is what? 4 is the max min. 4 is max min. Min means maximum of the minimum, best of the worst. And here the 4 is what? Here the 4 is what? It is the min max, means minimum of the maximum losses. It is the maximum of the minimum gain, and here we have the minimum of the maximum loss. So whenever we have this unique, right, this four, so their intersection will be the saddle point. So saddle point will be the 2 comma 3. Saddle point is the 2 comma 3, means the if the player A use if the player A use the second strategy and player B use the third strategy, then the value of the game will be the 4. 4 means player A will win by the 4 point. Player A will win by the 4 point if player A use any other strategy other than the alternative 2, then definitely this value of the game will reduce. If player B use different strategy other than the strategy 3, then definitely this value of the game will increase, right? Then the player will win by the more point. Clear this part? So here this is the value of the game. Value value of the game. And saddle point is what? Whenever we have the unique solution, then only we write the saddle point. So saddle point is the 2 comma 3. It is the matrix index where we have the value of the game. So whenever the uh, how you have determined the saddle point exists only when min max is equal to max min. Only then the saddle point exists, and it is equal to the value of the value of game. Min max is equal to max min is equal to value of the game. So, and here whenever we have the unique strategy, this is A2 is the unique, B3 is the unique, then we say it is the pure strategy problem. Presently I have not discussed the mixed strategy problem, it is the pure strategy problem, right? So in this way we solve. So same here we have done. So first we have computed the row min, and here we have computed the column max. From the column max, we have selected the min max, and here we have selected the max min, and their intersection will give you the value of the game and the saddle point. Similarly, if you let us see this second part. So in this case, what is the row min? Row min is the -5. In this, row min is what? -9. In this, row min is what? -9. In this, row min is what? -9. Then column max, here we have the 7. In this, again we have the 7. In this, we have the column max -5. And here we have the column max 6. Column max 6. So from the column max, this will be the min max, and here we have the max min. So when we have the max min and min max, so their intersection will give you this -5. So it is what? It is the value of game, right? And value of the game is coming -5. -5 represent that player B is winning by the 5 point. B is winning by the 5 point because presently we have the payoff matrix of the player A, and here the value of the game is coming minus. So it means A is losing by the 5 point and B is winning by the 5 point. So this is the value of the game. right? So and saddle point is what? Saddle point. So saddle point is the 1 comma 3. 1 comma 3. What this implies? This implies that if player A is using any other strategy other than the strategy 1, other than strategy 1, then definitely he will lose. Presently he is losing by the 5 point, but he will lose by the more points, by more than 5 points. And if player B is using the another strategy then other than the strategy 3, then definitely presently he's player B is winning by the 5 point, but as he changed the alternative other than the strategy 3, then he will win by the less margin than the 5 point. Clear this part? So here solution for the pure strategy problem. So this is the pure strategy problem. So it is not necessary always you have the pure strategy problem. We can have the mixed strategy problem also. So here we have the solution of the same. So from here, so in the part A, you have seen player A has been by the has won by the by 4 point, and in the part B, player A lost by the 5 points. Right. So from there we have the idea of the fair game. What is the fair game? If the value of the game is 0, then we say it is the fair game. Strictly determinable game means if it is of pure strategy, then we say it is the strictly determinable game. Means strictly determinable means we can decide strictly what is the value of the game and what is the optimal strategy. So if a game is strictly determined, the best strategy for each player is to use the pure strategy. Means but whatever the two examples we have seen, both are of strictly determinable game, because in that we have given you the solution, optimal solution in terms of the optimal strategy. So, and that is the uniquely and it is the pure strategy, right? So in general, player pure strategy means the players use the same strategy over and over. Let us have this situation question. The following game gives the age payoff. So both are the age payoff. Determine the value of the P and Q that will make the entry 2 comma 2 of each game as a saddle point. So you have to determine the value of the P, right? You have to determine the value of the P and Q so that 2 comma 2 is the saddle point. So this is the saddle point. So what we have to do? Here we have the row min. Row min can be either the 1 or q, because we do not know what is the value of the q. Here the row min can be the 5 comma p. Here the row min is what? 2. What is the column max? Column max. Column max can be the 6 comma p. 6 comma p, because we do not know what is the value of the p. So it is the 6 comma p. Then column max is q comma 5 or 5 comma q, 5 comma q, because we do not know what is the value of the q. Then column max, it is the 10. It is 10. Now it is given to you 2 comma 2 is the saddle point. If 2 comma 2 is the saddle point, it means this is the max min and this is the min max, right? This is the min max. So if it is the max min, if it is the max min, it means p must be this will implies p must be greater than equal to 5, then only this 5 is the saddle point. Clear? And in this case, if I'm saying that this is the min max, so it is possible only when the q is, it is possible only when the q is less than equal to 5, then only this 5 is the maximum. So for the first part, if p is greater than equal to 5 and q is less than equal to 5, then 2 comma 2 will be the saddle point and value of the game will become the 5. Similarly, if you see in the second one, so here the row min is what? 2. Here the row min is what? Can be 7 or q. Here the row min can be the 4 and p. Here the in the first column max, if you have to write column max, so maximum can be the 10, maximum can be the 7 comma p, maximum can be the 6 comma q, and it is given to you 2 comma 2 is the saddle point. So saddle point means value of the game is the 7. This implies that value of game is equal to 7. So
Excuse me, sir.
some some doubt? क्या?
Sir, in the first question, I had a doubt actually.
First part. Acha, let me finish this then. Right.
Okay,
So
sir.
here here we have the 7 comma q, and we want the 7 as a row min. So for that the q must be the greater than equal to 7, and here the p7 must be the max min min max. So due to the min max, it is the p must be less than equal to 7, because we are saying that it is this point is what? This point must be the max min, and this point must be the min max. Now please ask.
Sir,
Yes,
if
please ask.
sir, if 2 is the saddle point, here we must have Q as the column max of B2, right? So Q greater than or equal to 5, right?
Huh?
Sir, but we got
No, no,
Q less than or equal to
no, no.
5.
Column max we are saying na, column max.
Yes,
So
sir.
this is the maximum. This is the maximum. If we are saying that this is the 6, let's say it is the 6. So this will here we have the 6. So
Yes, sir.
then this 5 cannot be the saddle point, na?
Yes, sir. Got it.
Eh?
Yes, sir. Understood.
Understood, no? Can I change now? Now let us have this example. Two players A and B play coin tossing game. They are the two players. They are playing the game with the coins. Each player unbeknown to the other, means other do not know what he will choose. Chooses the head or tail. Both players would reveal their choices simultaneously. Tail, head, head. It may be any choice. If they match headed or tail, then the player A receive 1 from B. Then if both coins have the same, if, means same choice, both players have the same choice, then the player A will get the $1. Otherwise, A pays player B a $1. So player A has the two alternative. Player A has two alternative, either the head or tail. Player B also has the two alternative, head and tail. So if both are choosing the head and head, then the player A will get the $1. If both are choosing tail and tail, then the player A is getting the $1. Otherwise, he has to pay, that is the -1. He has to pay $1 to the player B, that is the -1. Clear how to write the matrix, payoff matrix? All in general we write the payoff of the player A only. Very rare we write the payoff of the player B. So what is our way to determine the optimal solution? We use the best of the worst. So what is the first? First we select the row min. So row min is the -1 -1. What is the column max? Column max, it is the +1 +1. So uh, now, if it is a plus 1, it means this is both are the min max. No unique min max. It is when we are choosing the best of the worst. So it is what both are the maximum. Both are maximum. So here, when I have said you, we have the pure strategy problem. Whenever the maximum is equal to for the pure strategy, for pure strategy for pure strategy problem, we should have the maximum is equal to min max. Maximum is equal to min max. But here, what we have maximum maximum is equal to what? Maximum is equal to minus one, minus one, and min max is equal to one. So they are not equal. They are not equal. So it is not a problem of the pure strategy. It is the problem of mixed strategy. What is happening here means if player A chooses the right, if player A chooses the head, then player B will select immediately. The player will select the tail. As the player B select the tail, player A chooses the tail, right? So if this happen, A can move to strategy 80 to reverse the outcome of the game by receiving $1 from the B. So constant temptation to switch to another strategy shown that pure strategy solution is not acceptable. Here we haven't the pure strategy. Means pure strategy means always we have to opt that alternative. But here we are not opting the same alternative. Depending over the opponent's alternative, we can uh, select the strategy, right, with some associated probabilities. So instead, the both player can randomly mix their respective pure strategy. So here we have to mix the pure strategy, either the head or tail for the both player. So we have to mix the two or more pure strategies. Depending over the question, we have to mix the two or more pure strategies. So in this case, the optimal value of the game will occur somewhere between the maximum or min max value of the game. Max values of the game. So here the values of the game always lie between these two, maxmin and min max. So for this question we have seen that maxmin is what? Maxmin is -1 and min max is what? It is the +1. So the value of the game will lie between -1 to +1. So it is not a pure strategy problem. It is the problem of mixed strategies. In the mixed strategy, we have to determine which strategy we have to use and what are the associated probabilities. Means we, because we use the pure strategy randomly, right? We use the pure strategies randomly. So when we are using the pure strategies randomly, means more than one strategies. When we are using more than one strategy randomly, so we have to determine the likelihood when we have to use which strategy. So here, let us have this question, a small question. Let Aij be the ijth element of the payoff matrix with m strategy for the player A and n strategies for the player B. The payoff is for the player A. Prove that. If payoff is given to you for the player A and A has the M strategy and B has the N strategy, so you have to prove this. So it is always true. It is always true. Max min is always less than the min max. So here you have seen max min is what? -1. Min max is what? +1. So max min is always less than the +1. So how you can prove this? So you know that min of Aij, min of Aij is what? It is always less than the Aij. Min of Aij always less than right, for over the j. So minimum of aij, row min is always less than the all entries of that row. And max of I, min of j of the aij is always less than max of I of the aij and this will be the max of I min over the j aij always less than min of j max of ij. So that is the right. So you can visualize this from the table also, payoff matrix also. So let us continue the same thing in next lecture. So today we have covered only the pure strategy problem. So in next class, I will I will cover the mixed strategy problem. Clear? Is there any doubt? So here and now I am stopping.